Hey everybody, this is my experiment 4. In this experiment, we're going to be dropping a magnet down an aluminum foil tube, and we're going to be looking at the forces on the magnet. So you can see right here, this is our model. We're just dropping the magnet down the tube. Aluminum foil is kind of like a coil, and the magnet is going to be the system, and the tube will be surroundings. So we're going to assume that gravity is the only outside force. The North Pole faces down. We start at zero velocity, and we're going to drop the magnet right at the top of the tube. So these are some formulas we need: the derivative of flux of a falling magnet, and then the force of the magnet on the aluminum foil, because that was going to ultimately be the force of the aluminum foil on the magnet by Newton's third law. So these are the measurements of the aluminum foil on the magnet. Magnetic dipole magnitude came from the experiment 3. So our brief results: we averaged 2.1 seconds falling in real life, and we simulated 2.9. So this is the code that we used to simulate. So this just takes the tube and divides it into a bunch of tiny rings stacked on top of each other. Okay, this is the first code we had to actually do ourselves. So this calculates the derivative of flux using the formula we saw earlier for the derivative of a falling magnet. The derivative of flux of a falling magnet we have down here, right here, and here's the numerator and the denominator, and this is the radius of the ring, of each little ring that we've divided the tube into. This is the distance from that ring to the position of the magnet, and this is the speed of the magnet. We're gonna have a while loop. So while basically the magnet is still within the big tube, we're gonna keep iterating through each ring and calculating the force that it is exerting on the magnet. To do that, we are going to get the magnetic field at that ring from the magnet, and then we're going to calculate the force on the ring from the magnet, and we're going to add all of those forces on each ring together, and that's going to be our total force on the magnet by Newton's third law, and you can see the code for that right here. And then we're going to take the F net, and that's going to be the force of gravity plus the force in the magnetic force. The force of gravity is just going to be the mass times the gravitational constant. And then at the end, we're going to update the velocity and position each time as the magnet moves through the tube. So these were our results. It took 2.9 seconds roughly, slightly longer than real life. You can see the graph over here. Still pretty close though. And if you notice the graph, you can see this speed increasing rapidly at first, but then coming back up and go into a constant speed. Yeah, we'll talk about that later. So here's just some checkpoints. We can't use something like a steel pipe because it would have stuck to it. We need something that's non-magnetic in order to do this experiment. And as the magnet falls, it reaches a terminal velocity. If it wasn't falling in the tube, it wouldn't reach a terminal velocity. It would just constantly accelerate and go faster. So as viewed from above, the red parts, which you can see right here, and there would have been blue underneath it. The red corresponds to a counterclockwise current, and the blue corresponds to a counterclockwise current, the North Pole facing down, viewing from above. This is because of Faraday and Lenz's law. You can look at the detailed explanation right there. If we were to flip the North Pole up and the South Pole down, it would just flip the directions of the currents, but everything else would ultimately be the same. So the real world and the simulation are pretty close to each other. To make the simulation more accurate, we could account for like where specifically like millimeters above you drop the magnet from. If you accidentally release it with any speed, air resistance, stuff like that could be taken into account, but that would be a lot harder to do and need cameras and all the types of other stuff. And then finally, the shape of the graph tells us that it takes a second for the induced force to kick in. You can see the shape of the graph right there. First, the force of gravity is initially the main force, but then the induced force currently gets stronger. So what if we sent the resistance basically down to zero, this would send the current to infinity, and we just send the force to infinity, so the magnet would kind of just float in place or potentially be launched upwards. If we were to cut holes through the aluminum, this would weaken the current or completely destroy the current in different parts of our model with cutting the tube into rings. And this would make the F net kind of bounce between 0 and non-zero as we go past these holes. So some sources of error could be calculations, formulas, code, measurements, not accounting for outside factors. This should be mentioned that I had to multiply the width and the inner radius by 2. So basically I had to use the diameter instead of the radius in order to get the right thing. I'm not sure what was up with this, but the one on the left gave pretty close results to the actual thing. So that was a source of error that I'm not sure where it came from. I looked for an hour, couldn't find it. But yeah, that's it.